Hello, and welcome to this webinar, Strategies for HPLC Method Development. I'll start off with some information about the webinar and how it works, and then I'll give you a little bit of an introduction to who I am. So as you can see, I have my webcam on and I've enabled my microphone, but you are all on a mute. And this is just for the purposes of webinars, the way that I set it up. If you were joining me on one of our live online training courses, then what we would do is use the webcam and the microphones throughout, because it gives us a lot better interaction. Also, because it's a webinar, we're going to keep all the questions to the end, so I'm more than happy to answer your questions. And if you have any, just type them into the public chat box, which you can hopefully see down on the left-hand side of your screen. If you have any messages at all that you want to share throughout the webinar, put them in there. And again, in a live online training, we just try and deal with questions as they arrive in a very interactive way. So it's just for the webinar, we do it slightly differently. Okay, this is me. My name is Oona McPolin and I will be running your webinar today. I'm the presenter and I am representing my business here, Mourne Training Services. This is a consultancy business. It's been running for about 13 years now, and as you can see from the name, it's primarily focused on training and training courses. So I run a range of courses on lots of different topics to do with analytical chemistry. I tend to focus much more on pharma, and I think most of the people here today are actually from a pharma background. But in HPLC, it doesn't really matter so much. So when I do HPLC training, it tends to be open to a much wider audience, and I get people from all sorts of different industries. So if you're not from pharma, that will work fine for today. Other courses that I do are things like validation of methods, transfer of methods, out of specification investigations, things to do with labs generally and managing those. Just to give you a little bit of background about me, I have worked in my industry, in the pharmaceutical industry, for over 25 years, mostly in a GMP environment, and very heavily involved in method development, method validation, troubleshooting, trying to keep those methods working. I also worked recently with EDQM and the European Pharmacopoeia, contributing towards chapters that are being published, hopefully draft quite soon. I've written a book on HPLC, so it's an introductory level book. It may not be suitable for those of you today who are maybe more advanced and ready for method development. And I do work with some other companies. So in my consultancy business, I do auditing and I also do consulting. So sometimes consulting is related to method development and HPLC, sometimes validation, a wide variety, just if people need help. And audits I do as well. So they're usually very friendly audits, just checking against best practice, helping people to make sure that everything's going well in their lab. So hopefully that gives you a little bit of an idea who's talking to you. In terms of HPLC, I have used it as my primary technique for over 25 years now. And I think one of the challenges that I had at the beginning of my career is how do you go about development methods and where do you start and what way will you attack it? So in my courses and today I'm going to talk about strategies, trying to deal with that, trying to make it easier. Who are you then? Well, we've quite a good attendance list, so I think we're doing quite well. There's always a tendency, sometimes things get in the way and you can't always make it a webinar that you've signed up for, but we've a good number of attendees today. Scrolling through your list, we've got a wonderful mix of international delegates. So the country list is quite large with people from Brazil at one side, right over to India and Jordan, right down to Nigeria. So quite a lovely mixture of people, and some more local to myself. I'm based in the UK, in Northern Ireland. So we have a lovely mixture of people on the webinar today. As I said, mostly we've got people from a pharma background, but not everybody. And I think just to give me an idea and to give you an idea of who else is here, this simple question will get us started. So I just want to know if you've done this yet. So have you actually developed a HPLC method? And I'm just going to put a little poll up so you can click on that. So just a simple yes or no. And that'll give me an idea of where we are in terms of, as we go through, how much data do you need? So we're getting up some no's, some yeses there. We have a few left to click in. You'll find if you're attending the webinar on a desktop, it's very easy to take part in the polls. If you happen to be using a mobile, it's a little bit more awkward because the screen's quite small, but the potential is there. So I'm going to publish that now. We've got nearly everybody. So we've got a bit of a mix. Majority is yes, but quite a few of you no, sort of roughly half and half. So I'll bear that in mind and try and adapt as we go through for both sides. So this is our topic, strategies for HPLC method development. And I've got a picture here of a chessboard and these lovely chess pieces from Lewis Chess Pieces. And I think one of the things about a strategy is that it gives you a plan, doesn't it? And I think the benefits of that in method development are very straightforward, so I don't have to sell you on why we use a strategy. And I think we would like something to help us get to where we need to be. So let's have a look at the challenges that give us the need for the strategy. Well, ultimately, this is our big challenge. We have a huge number of potential variables. So columns alone, there's hundreds of columns out there, aren't there? So we have hundreds to choose from. Then we combine that with mobile phases, solvents, pHs. Then we have the things to do with the instrument. So what detector will we use? And if we have a detector, what wavelength will we use? Or for other detectors, what strategy do we need to set that up? So we have so many potential variables that we can't try all of them. So we need a way of trying to reduce those choices and make it simpler. And the other issue is that with all of those variables, HPLC is the type of technique where it's very difficult to anticipate what you will get until you try it. So sometimes you can have a good guess. You can look at the structure, you can base it on your previous experience, and you can think, yeah, that'll probably happen. But until you've run it, you're never really quite sure what the separation will be. You might predict the order of peaks, but sometimes it might surprise you. So we don't really know what will happen, and there is an element of chance. So that leaves us to a very large number of experiments to look at everything. So our strategy that we're looking for, the aim is to maximize the success chance in the shortest amount of time and hopefully the least amount of effort. So that's what we're trying to achieve with the strategy. This is our starting point of what we're trying to achieve. And I've got this little picture which I love because it's my daughter, although she is a teenager now and she's much taller than me. But basically what I'm trying to say is the same strategy doesn't always work. So you will have different strategies for different situations. And if you can bear that in mind as you go into method development, that flexibility is very, very helpful. And it might help you to get to the best outcome in a quicker time. So let's have a look at the choice and what does it depend on? What types of parameters will make a difference? Well, the first one I think is fairly obvious. It's the sample. What are you actually trying to analyze? Is it a multi-component sample containing lots of different types of materials in there? And you are trying to maybe look at several components in it, or maybe just one, but what is it that you're trying to analyze? So that can be a very big, important feature. Is it a pure substance, which you would hope would be easier? Or is it something like an environmental sample? Or if you're in biopharm, bioanalytical, maybe plasma or a clinical trial sample, where there's quite a lot going on in there. And the next bit is to think about, well, what am I trying to achieve with the method? What is the requirement of the method? Am I only interested in one thing? Am I interested in lots of different things? So I might have lots of peaks that are important to me, or I could have just one that's important to me. And do I want to put numbers on these things? Am I trying to quantify how much is there? Or am I just interested in, well, what is it? You know, I'm looking for more qualitative data. I'm just trying to separate as much as I can. So those are very specific to this particular method development. And what I usually advise in courses is that you try and split your method up into maybe two very vague categories. You can go much further with this, just trying to give you a starting point idea. I've talked about a simple and a complex separation, and I've put them in quotes because it's quite hard to say there is any such thing, but that's what we're aiming for. It's just broadly, when you review the method at the beginning, you can make some deductions. So you can see, oh, I have a very small number of analytes. It's in a very straightforward sample matrix. I have good potential here of getting a method really quite quickly. I might just choose a particular column mobile phase, run it, and expect that it will work first time. If it doesn't, then I might look at some other conditions. Sometimes you look at it and you think, no, that's not going to work. So if we have a large number of analytes, what I mean by that is that there are multiple peaks in the chromatography that you're going to be interested in. If I have very complex sample matrix, or if I have something that basically I know from this first impression, from reviewing of what I'm trying to do, that it's unlikely there'll be a simple solution, then what I might be inclined to do is to screen and try and figure out, well, let's try a lot of different columns and mobile phases and see which one looks most promising. Before then, I take one of those in and look at it in more detail. So this is not something you have to do, but this is quite useful to try and give you a start of an idea. Okay, and while I say it there, I'll mention, yes, there is a handout to accompany these slides, and I'll show you how to get it when we finish. Okay, so just thought I would give a quick check and see what you have. So do you think your methods fit into either of these categories? Now, I'm suspecting that most of you are probably in the category of B here. Oh, I've put a yes, no, excuse me. I should have put an A, B, shouldn't I? Hold on, I will start again. Bear with me. There we are. That's better. So, do you think you fit into a simple or a complex category? And yeah, I think B has it here. Yeah, most of you are B. That's what I would expect if you're interested in method development strategies and you're coming on a webinar to find out more about them. But it's really good to consider this whenever you're establishing where you want to be for a new method, is try and figure out, well, which is it likely? So I think we will publish those, and we've got a very strong bias towards, complex methods. Okay. So the third thing that this strategy depends on is entirely over to you. The first two were about the situation. They were about this particular analysis. But the third one is very pragmatic. It's very much situational. It's just, what do you have available to you? What are your options? So I've picked out 4 things that are often a bit of a challenge, and you might have others to add to this list. So the first one here in this top corner is time. So how much time do you have for it? Is it very urgent? You need it yesterday. You need to find out as quickly as possible what's happening in your sample, so you need a method straight away. Or is it something that you have more time with, you have a plan in place, and you can take your time with, which is less common, let's be honest, but can happen. If we go downwards, first of all, and we look at availability, I've got a picture of a system and a column, so they're 2 good examples. But really, it's everything here. So what columns can I buy? Can I just buy whatever column I want? We used to be in that position many years ago in pharma. It's not really the position anymore. Or do I need to use a column that's already in the laboratory? Or is it something that I have, just using something that's been used before? In terms of reagents, what have I got access to? So have I got any solvent I want, or am I limited in terms of what's in my lab? And instruments. So we're assuming you have access to a HPLC, but do you have a UHPLC? What detectors are on the end of that system? That will have quite a big effect. So those are some of the things around availability. So it's quite a broad general area, but you will be constricted by whatever is an option for you. The next one, we'll just go on over here to the right bottom corner, cost. So this kind of leads into all of the other ones as well, doesn't it? Because cost relates to time, availability and expertise. But money, basically, how much have you got to spend? Because if money's no object, then you might try things that you wouldn't try if you're very much on a budget, trying to work to a budget. So that one is always going to be an issue. This is expensive. These systems are expensive. These columns are quite expensive. And it might not just be now when you're developing the method, but it might also be when you're running the method in routine use. So you might want to find a simple strategy for, say, sample preparation that is very quick and easy to do, compared to something that is more complex and has a cost associated with it. And this one I've left to last, expertise, because it depends on where you are in your personal journey of HPLC method development. Have you been doing it for years? Well, then you will try more complicated things. Are you quite new to it? We had a couple of people who hadn't developed methods before. Then you need to think about, right, at the beginning perhaps I'll take it a bit easier. I'll try simpler strategies, and as I build my expertise, then I will build up and look at some of these other options that are out there. So those are just some things. So again, what about you in terms of your particular challenges? Now, I've just put the four that I mentioned there, but obviously there could be others. So if you do want to type into the chat box, please feel free. So time's coming up quite strongly here already. And then we do have an availability. Just being able to buy columns is often a problem, but it could even be systems and detectors there too. We have some expertise, but I think time is coming up as the biggest one. Well, that's very reassuring from the point of view of my audience that cost hasn't immediately come up as the biggest one. Oh, we've got one. Okay, so there's a bit more. I'll just wait for a few more responses and then I'll show you what we've got. Okay, I think we'll show you now. So out of the people that responded, I think time comes up as the big one. So a little bit on expertise, and that's going to be very personal, so that sometimes applies. Availability came up, and then cost a little bit too. So availability and cost are quite linked, aren't they? So what I'm saying to you is that, again, be flexible with your strategy. Think about these things right at the beginning. Be realistic about what you have the potential to do at the beginning of your method development. Okay, the other thing before we look at particular strategies is I want to draw your attention to the fact that there are really two phases of our method development when we're looking at HPLC. And it's simpler to split these out whenever we're looking at different strategies because we might combine different approaches. So I would say phase 1 is all about setting the instrument up, because you can't do any experiments or start any method development until there's a column on that instrument and there's some type of mobile phase. Now you do have the option to change that mobile phase, to change the proportions, so you do have a lot more, but you need to put something on. So that's what I would refer to here as this phase 1. Now phase 2 then is where you've got a column installed, you've got some type of mobile system that's adjustable, and now you're trying to make those adjustments, and you might also bring into play other adjustments. You might bring temperature in, for example, see what it does to your resolution. So now you're just trying to find the optimum method conditions for this separation. So they're subtly different, but they can have the same strategy running through them. So if we have a little look now at some examples of strategies that we're now going to work our way through, you can see that some do go right through from phase 1 to phase 2, whereas some are just in one side or the other. So these are the ones that I've summarized for you today. First one, find a method in the literature. I think we're all familiar with that, so we'll have a look at that. Second one is a bit vague, but I'll just give a quick overview of this idea of trial and error. So that might be where you start if you don't know anything. A generic approach means using the same approach for everything, so that has some benefits, some drawbacks. If you're looking at a mobile phase and column choice, so initially, then screening physically through different columns with different mobile phases is a really good strategy to help you choose what looks most promising. This isn't really an optimization technique, so it's not in phase 2. And then DOE is interesting, design of experiments. So we've got this on both sides. So it's a screening technique, and basically it's statistical design that helps you to set up associated experiments. And we'll talk more about it in a little bit. So you can use this at both phases. It's quite a versatile tool. Once you're into phase 2 and you're thinking about optimizing, then changing a factor at a time comes into its own. So you try something, see what happens. You try something else, see what happens. So you're going through it in a slow way, but it can be quite powerful. Or you might want to just do a simulation. You can model your separation. There's software that can do that for you. So you would put all the data that you collect into a piece of software and it would create an in silico model. And that's very much an optimization tool. It won't tell you which column or which mobile phase to use. So I've just split them up a little bit for you. So what we'll do is go through these strategies. But before I do that, just want to make one comment. And my comment is about quality by design. Now, if you're not from a pharma background, I think most of you are, this may not be as familiar, but it is something that we have embraced very strongly in pharmaceuticals and pharmaceutical manufacturing. And the concept is that if you are working on developing a process, you design in quality by being very careful about knowing what you're trying to do. So we've predefined objectives. We have process understanding and control. So we know exactly what will be the effect of all of the parameters in that process. We call these our factors. And we base this on sound science, but also quality risk management. So this has been applied very successfully to production processes, not just in pharma, but in other industries. And what we've done with analytical methods is come up with a similar process for our methods. So it's applying quality by design to analytical methods. And the aim here, and what we would like in our strategy for method development, is to develop a better method that we can manage through its life cycle, and we can have that full process understanding. We've given scientific justification and ideas of why we've got to where we are. Something that you'll find if you look in the literature is pretty much always that I can find QBD and HPLC, it talks about DOE. So it's very closely associated. DOE does work very well for giving you quality by design methods, but it's important to realize they're not the same thing. It is possible to create quality by design methods with computer modelling, with even one factor at a time, with good understanding of what you're doing, and not use DOE, but still have QBD. So I think that's worth mentioning. It's worth making that point. Okay, so let's have a look through our strategies and review each of these in turn. So our first one, finding a method in the literature. I think we've all done this. It's fairly straightforward. You look up your molecule, see if it's been analysed before. You might have a sample type. You might have multiple molecules. Search engines on the internet are usually a good place to start. Maybe Google, Google Scholar, things like that. And the sort of sources we're expecting to find are things like journals, papers in journals. But maybe not only that, you might also have good success if you look at vendor application notes. Sometimes they know you want to analyse a certain thing because other people are doing that. So they put a lot of resource into creating methods on their products. They can be quite helpful. If it's an older compound or it's an older technology, you might even find a textbook or a modern textbook can work quite well. And you might also use a standard method. So in a pharma industry, we would maybe look in a pharmacopoeia. But if you're working in environmentals, you might look at the EPA lists. So you might have standards for the things that you're trying to do that can be helpful, if not actually giving you a final method. So let's have a look at the pros and cons. The obvious benefit is that the work's already been done. We like that. That would be good. We can have a method without very much effort at all. The downside, I'll go over here first of all, is that it doesn't necessarily mean it's very good. So you don't know about the capabilities and understanding of the person who developed that method. I see a lot of methods in the literature that are really quite awful. And what you could do is create something much better in terms of resolution, separation, on more modern instrumentation, maybe using a UHPLC, maybe using much quicker and cheaper reagents and instruments. So it's not always perfect. Other downsides, it might not be suitable for your sample. And if you're working on something quite new, it's unlikely that that will be in the literature. So you're working from scratch. But this bit's quite interesting here. So I would say even if you don't find a method, it is a very good starting point. So what will it tell you? Well, it'll tell you the type of HPLC. If somebody has analysed this before, does it work with reversed phase HPLC? Does it work with ion exchange? Did somebody get it to work with helic? So immediately you have that comfort of knowing, yeah, it works there, because I wasn't quite sure. Perhaps it's a borderline type of molecule. You might also know about the column, the stationary phase. So you know, oh, it works with that. And if you're lucky, you might even have some chromatograms. It doesn't mean you'll necessarily choose that exact column. But if it's worked on a C18, you might have a good idea, well, that should be similar to the one I'm going to use, so I can do that. Other things are things like detectors, perhaps you look at the structure of your molecule and you think, is there a chromophore there? Is it a strong chromophore? Is it going to absorb UV? You're not sure. You find someone else has done it. So that really helps. Or if it doesn't have a chromophore, what you might find people using other types of derivatizations. So you could find some useful information there. So mobile phase 2, the solvent and the pH, see what other people have done. The sample prep, I mentioned derivatization, but it could be other things. It can be really helpful to see what other people have done. And also the sensitivity of the method. So I find this quite useful when I'm doing literature searches to support customers sometimes to see, well, what level did other people get? What signal to noise did they get? Is it going to be fit for what I wanted to do? Am I going to have to think again? So that can all be really useful. So what I would say to do with it is, if you have the ability to search the literature, do so. So you've got a well-known molecule and sample that you can expect to find something. And then combine it with other strategies. So it's great just for gathering lots of information, even if you don't use the method that the person in literature did. Or if you haven't a lot of experience with method development, it could be a great way to start, to begin. So you could say, okay, well, I will use their method. I'll see how that goes. Now, the idea of a paper, obviously, is so that somebody else can follow that and get the same results as you. But you might find that doesn't always quite happen the way you expect. So occasionally you might struggle to get a method from the literature to work. So I just wondered, from your point of view, is this something that you have done, either to find your final method, or it could be that it was to just gather information. So either of those, and we've got lots and lots of yeses on this one. So as we would expect, I think. So we have one person who's quite new to method development, so that could be our no. But generally, yeah, we've got almost everybody now has put up an answer. Okay, let's publish that. So we have got the vast majority of the answers were, yeah, we've done that. So we're familiar with that. So that can be a really useful thing. Okay, next one, trial and error. And basically we're saying here, try a set of conditions and design your next experiment based on that outcome. This is kind of how I play chess. We had the chessboard earlier. I'm a sort of see what happens person when I play chess. I'm not very good at strategy in chess. It's not really a plan, but could be effective. But if you can think more moves ahead, you definitely will have a stronger strategy. So in terms of our separations, yeah, this could be effective if you came into that simple category that we looked at earlier. Pros and cons, very straightforward. You can easily react. But if you did this for all of your method developments without a more clear plan of strategy of what way you're going to run with these trial and error, it can be very, very time consuming. So ultimately you're hoping for good luck in this situation. So I would say combine this approach with other strategies. So I'm going to look at one factor at a time, which in a way is trial and error. But if you do that in a very structured way, it has quite a lot of power as a way of developing methods. The other thing to mention here, though, is that if you have a lot of experience in method development, you might just look at a method and know that's going to work straight away. So you might do a trial and error that's maybe 2-3 experiments just based on your previous experience. So sometimes that could be a good thing to do. And again, we've just got trial and error. Is that something that you've had a go at in any context? And yeah, we've got a lot of yeses. So this is something that we do. We're curious as analysts, aren't we? We just say, what does this button do? So we just try something, see what happens. And sometimes this is a really good learning technique. So in the point of view of, yes, you want to develop this method, that's your primary objective. But the other thing that you probably quite like to do is just learn more about how HPLC works. And I know when I started off my career, I was always doing this. What does this do? Try it, see what happens. So you might do it for that reason. So we've got predominantly yes, but a few no's. So something to consider, but a better strategy is good for good results. Okay, what about a generic approach? So the idea with this is that you always use the same starting point. So you have a favorite column and a preferred set of mobile phase conditions. And what you might combine this with is some type of scouting gradient. So if it is Hillock or it is reverse phase, these are straightforward ideas of very long range gradients. And there's a lot of literature on how to do this. So the pros and cons, well, it's very straightforward. And it could work quite well if you always have similar types of analytes, which might be the case. You might be working in similar compounds all the time. It does use the same column and reagents if it works. So that can be very convenient, because if you always use the same column and it works, you get to know it, you learn a lot about how it performs, you build a relationship with the supplier, you get a cost reduction because you buy so many of them. So there are a lot of pros to using the same sorts of reagents. But the other thing is, it's a good starting point to start in the same place, even if you don't end up always using exactly the same conditions, just to begin all of your method development. The downside, of course, is that it doesn't work, because if you just stick to the same thing and nothing else, it won't work. And what I'd say here is that if you don't even look at the molecule and just try it straight away with this generic approach, you might miss out on something. So it might be obvious if you just took a closer look that, there's no chromophore, this is not going to work. So flexibility is good in these strategies of trying to put a lot of them together into one overall. When to use it, I think personally it's a really good starting point for method development. So start in the same place, but allow yourself then to move up into different options using some of the other strategies I'll talk about. Is this something that you do? Because some labs swear by this and just do this all the time. So again, just wondering, get some idea of what we have. Yes, so lots of you do use a very similar approach. Everybody, in fact. Awesome. Okay, so I think 100% of our responders say, yeah, this is something that we've tried. It's just a generic one. I think it's a good idea, a good strategy. Okay, screening then. So here we're talking about looking at potential conditions to see which is most promising. So this is where we're thinking this is not simple. This is a complicated method, and maybe if I try lots of combinations of columns and mobile phases, I'll get some idea of immediately which one looks best, rather than doing them one at a time and going through lots and lots of different things. So these are the sorts of things we might look at, but you could include other things to this list. But columns and mobile phase are usually the key two we're interested in, because remember, we're going to optimize the other things very easily on the instrument. So we would optimize afterwards. So here's just a very simple expression of one of these experiments. So we've got 3 different columns. We're going to run that column with both acetonitrile here and methanol, and we're going to try it at different pHs. So this example, and I think a lot of my examples, are really aimed at reversed phase HPLC. So you might have slightly different types of approaches for other types of HPLC. Another place where we routinely screen would be chiral HPLC. So it would be a similar idea, but a different type of experiment here. So if you did all of this, you could see that you have 18 possible combinations. So that's quite a lot of work if you go down this route. And that's only 3 columns screened. And the other little proviso in this particular example is that I've put them at high pH, all 3 columns. And that does assume these columns will work on a reverse phase system with this high pH. And sometimes they do, and we choose them for that, and sometimes they don't. So these types of approaches are quite time consuming. So what you might do, and lots of companies do this, is have a system dedicated to this work where they have got a column switcher and maybe a solvent switcher as well. So in this layout we've got 5 different columns, and we can switch between these automatically. We can program this into the system, and we can also maybe program in solvents. So for our previous little example where we had 3 different pHs, what we might do here is on this A line have different concentrated buffers that we then mix through this mixer with water, and then our acetonitrile for that experiment, our methanol for that experiment, and we can automate the whole thing. You still have got quite long run times, but the advantage of doing it in an automated way is you just leave it running. So I've set up these in the past. I had a system that did this very thing, and you could just leave it over the weekend and come back, and you'd have a lot of data to trawl through. So I'm not pretending that was easy, but the automated part meant it just ran. I didn't have to attend it. It just did what I needed it to do, and I could look through the results at the end. There's even some automated packages nowadays that will look through those results for you and pick out the best ones automatically. So AQbD Labs, for example, make a product that does that. So our pros and cons, well, it does allow us to investigate all of these different possible combinations to find something that's promising, so that when we then go to optimize it and use some of our other tools, we're in a position of feeling quite confident that, yeah, this looks good. We're not looking at something that has no hope. The downside, of course, is the experiments and the time involved, and the equipment. Maybe if you do automate it, it's a pro, you can have an automated system, but from the con point of view, it maybe is a bit more expensive and you'd have to fit some sort of column switcher and so on. And it is just phase 1. So we still then have to take these conditions through and optimize and see, does this work? So we haven't established it will definitely work always at the end of screening. Sometimes we have, if we see all the peaks that we think we're interested in the initial screening. Now, they can be really fortuitous, but doesn't always happen. So I would say when I would use this is if you have something you know is complex and difficult. So what do I mean by that? Well, you've got lots of analytes in your sample, especially if those analytes are quite similar in structure. So we use this very often for impurities methods. And it could be that you have multiple potential interferences as well. So there's just a lot of things in your mixture, and okay, you're not interested in all the peaks, but you have to make sure that the peaks you're not interested in are resolved from the ones that you are. So there are some of the times when I would think about using it. This one, have you ever used it? I think we might have a bit less this time because it's a bit awkward to do. So we've got more no's this time straight away. Yeah, so far in our responses, it's mostly no's, I'm afraid. I'll just give a little bit more time. Okay, so if you publish that, we've got one yes, but mostly no. So I would say it really depends on what you're trying to achieve from the method. It's a great strategy, but it takes some effort. Okay, DOE then, I've already mentioned design of experiments. If you haven't come across this before, it is, as I mentioned, a statistical tool that allows you to design experiments where you're going to simultaneously investigate factors. So you're going to look at things at the same time. So that's very powerful. But as you can imagine, it's pulling out the information that is the challenge, because your chromatograms then are a bit mixed up because you're looking at 2, 3, 4 different things at the same time. So we need suitable software to do it, to do the statistical part, to do that difficult interpretation. So that's one of the things that is required. But it's a very flexible tool in terms of how we use it. So you could use it in screening. Now, generally DOE is called a screening technique, but that's statistical screening. So what I've been talking about so far is screening columns. So these are slightly different. I apologize. It's the terminology gets a little bit complicated. So when we're looking at screening columns, we could use DOE. We can also use it to optimize, to try and get the best conditions, and we get a design space for our method, which is very much in keeping with AQbD, which is why this is so popular. But we can also fine tune our method and pull in the ranges and then do another study to look at robustness investigations as well as the precursor to validation. So quite a powerful technique. Now, I did a literature review before I did put this presentation together because I've updated some previous work that I've done. And if you do a Google search on using DOE for HPLC method development, there is a vast number of publications and resources out there. And some of them are quite good, some of them are a bit vague and a little bit questionable, but quite a lot of work in this area. So that's what I mean by factors reported. So people have looked at, most commonly I think, it's getting the mobile phase composition right. So it's about optimization and looking maybe at pHs, compositions, maybe temperature in there as well. There are others that work on flow rate, column length, wavelength, more things to do with your choice of column here. So a lot of options really in this. Pros and cons, well, obviously it allows you to get there quickly because you've got this simultaneous investigation, so you save a lot of time and effort. You do, as I mentioned, get this design space. So ultimately that tells you within which area your method works. So rather than having one value for a factor, like a composition of mobile phase, you have a range of where it could work. That can lead to problems later on when you're trying to define the method for the analyst who needs to follow it, but it's a very powerful tool for troubleshooting and understanding of this method, which is what we want. The other thing that you might be able to get, it depends on the design, is to see interactions. Because sometimes factors interact, and if you go one factor at a time, you don't see that. So something like pH and temperature often interact and move peaks. But if we do just one at a time, we won't really see that interaction. So sometimes it's not always easy to pick up on a DOE, so I won't promise you too much here, but it is possible. But the downside is that you really do need to understand two different things. You need to really understand chromatography and how the particular type of HPLC you're using works, because you have to select factors, which thing you're going to investigate, like pH, for example, or temperature. But you also have to decide on the range you're going to investigate. So that requires a lot of knowledge. But the other thing you need knowledge about is the statistical software as well. So that's quite challenging. Now, I think in terms of my when to use it this time, if you have this knowledge and experience, go for it. If you think you've got quite good experience, but you're not sure you're ready, have a go. If you've got availability here, if you are able to use that software. And the benefit is that you don't have to make it really complicated. So you could do quite quick DOEs to prepare very simple methods, or you could do much more involved and complicated DOEs to do really complicated methods. So it has lovely flexibility if you are able to use it well. So again, I wonder, has anyone here actually got their hands on this type of software and had a go? So we've got a few people, so it's coming up that we have a few of you, which is great, and a few haven't. So we've 4 left. I think some people aren't able to join the poll, so I'll just publish that. So we've got mostly no, which is not that surprising, but a couple yes. So hopefully those of you who've used it will agree with me that, yeah, it's great, but it's not easy, is it? It's a bit tricky, so you need to know what you're doing. Okay, last one then. Oh no, 2 more, sorry. We've got changing one factor at a time. So it's a bit like trial and error, but what I'm trying to imply here by giving it a separate section is it's a bit clearer in terms of strategy. So we're looking at one factor, evaluating that before we decide what to try next. So what sort of strategies? Well, again, I've taken my examples from reversed phase, so I hope that suits most of you. And if you're doing a method development by reversed phase, one of the things you want to decide on is if I'm going to do it isocratically or I'm going to do it using a gradient. And my strategy for isocratic might have to be, I'll start with a very high amount of organic in there, because if I don't, I won't really know when the last peak has come off. So I don't know how long to leave it. And I don't want carryover from a late eluter in my first injection coming into the next one. So usually you have to start with quite strong solvents and then see whatever is in your sample and then reduce it and then reduce it. And this is just an example where it's jumping quite dramatically by 20%. You might do it slightly less than that. So it's one step at a time, looking at it, see what happens, then doing the next experiment. And if you're doing a gradient approach, we'll probably do a long range gradient, but when we get that far and we go to the next step, we might change the time of the gradient. So we change that incrementally, one factor at a time. And this is the little order of experiments I usually recommend when you're doing this approach in method development. So you'd start off with %B or gradient, whichever method you're using, whichever type of method, and you would change that to try and get the peaks to become more separated until at some stage it's just not really doing anything anymore. So then you're one variable at a time would maybe be looking at temperature, try an effect of that. Organic solvents, to changing over if you were trying acetonitrile to methanol. Mixing those, pH changing, and then your next step might be a column. So this is just a very typical type of one factor at a time approach. Pros and cons, it's good control. It's straightforward to interpret your results. So it has a lot of pros. It is quality by design if done well, because you can see exactly what's happening. It's good scientific knowledge. Problem is it can take a while. So it can take a long time. And if you have a very complex separation, that could be really difficult. So when to use it? I think if you don't have DOE or the next thing I'm going to show you, computer modeling, then it probably is the best thing that you can use. But if you did have computer modeling, that's probably an easier way to optimize a method. Or if you want to use DOE, that's probably an easier way too. So again, one factor at a time. I guess this is probably something that people do. It's a bit like our trial and error, and we got lots of positives in that one. So again, yep, we've got lots of positive responses. Okay, so we've got nearly everyone. I'll just publish that. Okay, so mostly yes. This is our final one then, is computer simulation. And this is for optimization, so we saw it in the phase 2 side of our method development. What we do is create a model by running a limited number of experiments, and we put this data into a specialist software. And some of the software that's out there, there's DryLab, one of the forerunners. There's LC Simulator from ACD Labs. ChromeSort also does it. And there were some other packages out there, so there's there's a few of them. What do we model on? Well, this is reverse phase. It's aimed at. So we've got %B, time of gradient, temperature, pH. You can combine things, so you could look at the gradient and the temperature, or the gradient and the pH. But the number of experiments is usually about 2 here and 4, and maybe for pH 6. So not a huge number of experiments to build the model. And there's just a little example of a screen capture from the way that this looks. You have a lovely user interface where you can see you've got the chromatogram, and you can change the conditions up here. You see there's a little gradient table, and that will allow you to see what effect it has down here in the chromatogram. And then this wonderful colourful display is a resolution map, which allows you to pick points in that map where you have the best resolution of your peaks, and that will help you to find the best method to separate the things that are important to you. So pros and cons. Well, the pro gives you this model with a relatively small number of experiments, and therefore you can get your optimization done virtually. And the other thing you can get from this is once you've got a method, you can adjust things slightly to get some robustness information, which I find quite useful. The downside, of course, is the software, and it's quite hard to give you a cost on this because it's very difficult. The manufacturers don't like to say how much it costs. It's very dependent on licenses and so on, but it is quite expensive. And if you think about running these experiments, the key thing you need to use this is to say where a peak moves underneath the different conditions. So you have to be able to identify the peaks. So tracking those peaks can be a bit challenging. I had the fortune to use MS on the end of my system, which made it a lot easier. You can use diode array with some success. You can adjust the size of your peaks, but it's not always simple to track them with complex mixtures. And my advice on this one, if you have it, use it. So not everyone has access to it, but if you have it, it's brilliant for optimization. So again, has anybody got access to this software and how to go with it? Mostly no's this time. And on most of the training courses that I run, that's what I find. So I tend to focus on the one factor at a time. And I think the beauty of one factor at a time is it does give you a really good understanding of how the method works. So hopefully then if you did get access to DOE and you did get access to computer modelling, you would be able to have a go and to use it. Okay, so nobody there has it. So to finish off, I'm just going to summarize a suggestion for a strategy that gives you sort of a combination of what we've looked at so far. So some of these ideas. So I usually suggest you start off by thinking about those 2 questions we had at the beginning. What is in your sample in terms of analytes, and what are you trying to do with that sample? So what are your goals? It makes it nice and clear. It doesn't take that long to do, but it helps you to set your objectives of exactly where you're trying to get to. So this fits in with this QBD idea as well. Next step, what do you already know? So here it could just be in-house information, but it could also be this literature search. Find out as much as you can about structure, about how these molecules behave, has anyone else analysed them, any information that will help you when you set up your experiments. It's solubility, all sorts of information. If you prepare well, it should shorten and reduce the number of experiments you do. The next one we haven't really touched on, we're talking about strategies, but this is just about something to inject. We need a little vial here to put onto our system to inject. So we do have to think about what will be in that vial. So we want our analytes in there, yes, but we also want interferences. So very often there isn't a single vial that you just inject and develop your method. Very often there's 2 of them, or maybe even more, that allows you to pick and choose which things you're interested in. Conditions then, I say, is just a general thing here. It's mobile phase and stationary phase. So how am I going to set up the instrument? I'm ready to inject the sample. How am I going to set it up? So a generic approach works quite well here, but you can be flexible with your generic approach based on that step too, because there's certain things you'll identify that will work and won't work. So it allows you to modify your generic approach. And then we're ready to do some screening if necessary. And then finally, we're into optimization. So our strategies here are one factor at a time. And if we have the option of it, maybe DOE and maybe computer modelling. Okay, so that just gives you some ideas around strategies. And a summary of what we've covered is that the best strategy will usually depend on that situation. Your choice of strategy depends on the sample, the requirements for the method, and your available resources, those 3 things we picked up. Different strategies may be required for your 2 phases. Remember I talked about choosing the column and mobile phase, phase 1, and then finding optimum conditions, phase 2. And I find, as hopefully you've taken from everything I've said, that a combination of these strategies works best. Being flexible, trying to build them all in. That's the idea of that 5-step strategy, is that it builds in all sorts of different ideas and strategies in a flexible way. And that DOE and computer modelling, very powerful tools in your method development, but they do require specific software. So you do have to have that plus experience to be able to use them well.